Okay, so what is the difference between an acid and a base? Well, basically, in most general terms, an acid is any substance that is a proton donor. A proton donor, something that produces H plus ions. It can also be termed as an electron pair acceptor. And a base, in very general terms, is a electron pair donor, or it is a proton acceptor. For further explanations on the types of acids and bases, meaning is it an Arrhenius acid, base, a Bronsted-Lowry acid or base, or a Lewis acid or base. For these questions, please refer to my other video referring to the different types of acids, the different types of bases, Arrhenius, Bronsted-Lowry, or Lewis. But for this video, I will just stick with simple acid-base definitions. Okay, so let's look at some very basic equations dealing with acids and bases. Let's first of all just take a look at HCl, hydrochloric acid, plus water. Obviously, I named this hydrochloric acid, so you already know it's an acid. But let's just say you didn't know it was an acid. Well, you have to figure out the Lewis structure. That will help you designate whether it's an acid or a base. And this is water's Lewis structure. So, when you analyze an equation, you will look at the protons. Well, all we know is that this is going to be our acid because chlorine really wants to be chlorine and -1. It wants to take all the electrons, or the electron from hydrogen, and make it a complete shell. Meaning it wants to do this. It wants to take that electron and keep it in the chlorine, near the chlorine atom, because of chlorine's high electronegativity. And hydrogen will be left alone. All it will have is a proton. Chlorine is negative here because it took that electron from hydrogen. And hydrogen has become net positive because it lost its electron to chlorine. So we know this is going to happen, and this obviously is a proton. So this can be a proton donor. That's why hydrochloric acid is an acid, because it is a proton donor. It will give this proton to water. So water is going to be the base, and part of our definition of bases was a proton acceptor. How is it going to accept a proton? Well, it has to have a lone pair of electrons, and it has 2 of them, but we'll choose just one of them. So this one here is going to grab that proton, and it will form this compound here. Because it accepted a positive charge, which is the proton, and this because water was a neutral species, so since this neutral species grabbed a proton, this is going to have a positive charge. Again, this was the proton that was from the HCl. So again, what happened to the other product, which is just going to be the chloride anion, which is very happy to be like this. Again, chlorine minus. So the base accepted the proton, and the acid gave away the proton. So your products are the hydronium ion. This is called a hydronium ion plus the chlorine anion. Okay, let's take a look at another type of reaction. Here we have our hydrochloric acid again. We'll have a different type of base. This will be just ammonia. And the products will be where ammonia is going to take its lone pair of electrons and grab this proton. And the two electrons here that are bounding the hydrogen and the chlorine atom is going to stay with the chlorine. So your products will be again, I will write it out Lewis structure-wise so you can see what is really happening. So this lone pair of electrons is going to grab the hydrogen. The electron will stay with chlorine. And so you'll have an ammonium ion here. Positive charge on the ammonium ion because it grabbed a positively charged proton. And the chlorine anion will be left by itself. So this is ammonium ion. Okay, so how about this reaction? Well, let's put it in Lewis structure diagrams so we'll see what's going on. So this is the Lewis structure of aluminum trichloride. And this is the structure of ammonia. Now, ammonia here is going to act as the base. It will actually donate a pair of electrons to aluminum. Aluminum is going to be an electron pair acceptor. It is not going to be a proton donor. It does not have a proton to donate. But still, this is a definition of an acid also. This is termed a Lewis acid. A Lewis acid is an acid that will accept a pair of electrons. It does not have to be a proton donor. So it will accept the pair of electrons. So it will accept this pair of electrons from the nitrogen. And the reason why it will do is because aluminum is one of the few elements in the periodic table that can handle 6 electrons around it. Most, as you remember, most nonmetals want to have 8 electrons and follow the octet rule. Sorry, aluminum and boron are 2 metals that are perfectly fine having only 6 electrons around them. But given the chance, they will form 8 electrons. So they're stable here, and they're also stable here. So this aluminum can take another pair of electrons. So that's why this is going to happen. Therefore, then what is the products? Well, the product is very simply, it'll be aluminum. This is the bond with the nitrogen. Okay, so this is the product right here. And in chemical formula form, you will just write it out as aluminum and then NH3Cl3. Or sometimes I've seen it as this. That is your product. Okay, so let's look at another type of reaction. Sodium, hydrogen sulfide, sulfate, and ammonia. So we know that this species here, this one here, is really in aqueous solution, sodium plus, and I will write out the Lewis structure for the hydrogen sulfate ion. Okay, so this is the Lewis structure for hydrogen sulfide, I mean. And then we have the Lewis structure for ammonium. So ammonium here is going to be the base. It is not going to be the acid because it will not donate these protons. That's not going to happen. So this is not involved in any type of proton transfer. Why? Because the nitrogen is very electronegative. This is a very electronegative. It's a very electronegative species, and that is so that will not give up those 2 electrons. And hydrogen is very closely bound to the nitrogen. So that is not going to be the proton donor here. So ammonia will be the base, and so that this will be the acid then. Since this is the acid, there's only one proton here that can be donated, and it is this proton, that one there. So this lone pair of electrons is going to take that proton. Well, let me write out that. So let me write that out again. So this electron pair is going to take that proton. Those 2 electrons here will stay with this oxygen. So your products are just going to be NH4 plus. Sodium is going to be just a spectator ion, and then you'll have SO3 2 minus. Okay, so that is your equation. Now let's say we had the same reactant here, but we now are going to hit it with hydrochloric acid. The products from this reaction is that this will be the acid and HSO3 is going to be the base. So the acid is a proton donor, the base is a proton acceptor, so your products will be H2SO3, the chlorine will be a negative, plus the sodium. So let's just look at this more closely. Again, the reactive species here is HSO3 minus. And if we write out the Lewis structure again, this is now going to be our base, and here's hydrochloric acid. This is the proton that will be leaving this hydrochloric acid, so the lone pair of electrons here will grab that proton. These two electrons will stay with the chlorine. And so that's why you can get this as your product. Again, the sodium is just a spectator ion. It does not change chemically at all in this reaction. It's just there to even out all the charges. So writing out the Lewis structure for the finished product so that you can see it. So basically, this is your H2SO3 product. So when we have a substance that can both act as an acid or a base, depending what it is mixed with. So here, this can be acted as an acid or a base. This is called a amphoteric compound. It can be an acid or a base, depending on the nature of the other reactant. So I'd like to give out one more example of an amphoteric substance because it is very important for us on planet Earth. It is water. So water is definitely an amphoteric compound. It can act as an acid or a base depending what it's mixed with. So for example, if I have water plus a strong acid, this is hydrobromic acid, water will act like a base, which means that the acid is going to donate its proton to water. Water is going to accept the proton. So water is going to accept the proton, and then you're left with the anion. So again, just to draw the Lewis structure diagrams to help you see what is happening. So here is hydrobromic acid. So the lone pair of electrons of water is going to grab that proton. These two electrons here will stay with the bromide, and that's how we get our hydronium ion. Hydronium ion has now a plus charge because it accepted the proton of HBr, and bromine will be now a negative ion because it kept the electron that was bonded with hydrogen. Okay, so that is when water is acting as a base. Okay, here in our next example, water is going to be acting as an acid. It'll be donating its proton to a base. So let's put SO3 2 minus. This is our sulfate anion, which will be the base. So the base will be grabbing, it's going to have a lone pair of electrons, it's going to be grabbing a proton from water. So we have remaining that plus HSO3 1 minus. So again, I'll draw the Lewis structures. Okay, so the lone pair of electrons on one of these oxygens, let's say this one, is going to grab a proton. The two electrons here that are bonded between the oxygen and hydrogen is going to stay with the oxygen. So again, your products are going to be it's the hydroxide anion, and here is your bisulfate anion. This is still an anion also because it still has a negative charge. It went from a -2 to -1. Okay, so that is an example of water as an acid with a base. So again, water is an amphoteric compound.